Good morning, good afternoon, wherever you are joining from. Welcome to the oral session 3.5, which will cover three presentations in the radionuclide area. My name is Hakim Bidou. I am the radionuclide officer at the CTBTO IDC. I have my colleague Bosch Will you for taking questions and answers after each presentation. Then the second part will be covered by other colleagues, and it will be dedicated to SHI part of the session. So in the radionuclide of explosions with selected results. That's by Dr. Harry Miley and his team. We have a pre-recorded video for that. Please, could you stream the video live?
Good morning, evening, or afternoon, depending on wherever you are. I'm Harry Miley, and I'm here today to talk to you about environmental backgrounds and their impact on the IMS. This was originally going to be Xenon only, but we added aerosol, and we think that's pretty interesting. So why don't we get right to it? We concluded that the backgrounds come as two types, things associated with natural radon in the atmosphere. When it decays to lead-212, that can impact the minimum detectable concentration of aerosols very, very badly. Xenon systems are much less impacted, but nuclear activities can emit the exact isotope we're interested in, and we created an anomaly level to say if something is above the 95th percentile of the background, we'll call it an event, and below that, we'll say we don't know enough about it. So this is a naive approach because we're only looking at one isotope at a time instead of ratios or anything, but we had to start someplace. So our anomaly level is the same as the MDC for a low background station. So most stations in the world are really unperturbed by background, and the remainder have an anomaly level at 95th percentile. Only a few stations even can have a defined anomaly level for iodine-131 because so few stations are affected. Let's have a look over here. We're also going to look at a wide range of source terms, but my favorite one to talk about today is where we have a 1% xenon release and a 10 to the minus 5 iodine release. Now this is a made-up case. This is probably not a real-world case, but it's illustrative, and we'll work an example of that a little bit later. Our conclusions are that xenon background is global and major, and that iodine background is regional and minor. And new results that fall out are we estimate the number of reporting stations and the reporting samples for a wide range of possible source sizes anywhere on the globe, and we identify potential background study locations. So let's get to it. If you go back a few years, working paper 224 defined what the network ought to be composed of and what its sensitivities might be. There were other definitions of these things, but that was the original one. We later defined a 10% leak of Xenon-133 to be the interesting one at 3 days of decay of iodine into Xenon-133. But we know that of aerosols, although working paper 224 was pointing at barium-140, we know that iodine-131 is the most likely to be released. There were 1,234 detects in the IMS over 9 years, and we're now at about 1 per day. That's actually not that many. If we look back at experiences in Nevada, the tabulated total releases for all kinds show that iodine was the same order of magnitude as xenon. Now we think the xenon systems were not that sensitive back then, but they're sort of on a par, but far ahead of things like molybdenum and barium, which are what we call refractory or not volatile things. But if we look over those 9 years, we see most of the iodine releases are quite small. So there is something there, it's of importance, but there's not very much of it. I guess that's a definition of a good background. Historically, the working paper 224 people nailed performance of the aerosol system. If you look at our calculations here, you'll see that our calculations for 39 and 79 stations bracket the calculations they did for 50 and 75 stations, showing that for a specific transport time and so forth, they really got it right. why did they get it so right? Well, there were a lot of systems in use, not globally, not in a network, but there were systems in use, and they could look at those examples. And in fact, they got the number right within about 1%. But no such record in the literature existed for Xenon. So I think that's been tougher to get right what the Xenon MDC was going to be in the real world. Now, word about notation. We created a new notation where we say this quantity DMN is the detection probability for a signal of magnitude M for a network with N stations. So examples, D1179 is a detection probability for a 10 to the 11th Becquerel release in a 79 station network, and delta D11 is the change brought on due to backgrounds, the delta caused by backgrounds. We're working on a location metric, and it's going to depend on the location, depend on the number of stations and the samples involved in the detection. So what we tell you about number of samples and stations is kind of a preview for what that's going to be. So let's get right to it, and let me get myself out of the way. What we see here on the left is for a very small release, a 10 to the 11th Becquerel release of iodine-131, and we see the network coverage on the left is actually not that great, but it's a terribly small release. Okay, now why did we choose such a small release? And honestly, the reason we did this was to make the apparent impact of the iodine on the network as large as possible, and it's actually still quite small. Okay, so this background effect would have been smaller if we'd chosen a higher Becquerel release. Okay, now let's look at Xenon. Here's the detection sensitivity for Xenon in the case where we have a 10 to the 14th Becquerel release. So that's a fairly sizable release, as it turns out. And this happens to be for a 79 station network, but actually the story we tell here is the same, whether it was 79 or 39, that the world looks pretty green, that is, coverage is pretty good, except when we look at the backgrounds over here, they cover a wide region. If we took the signal size down, the D14 to D13 or D12, then the red area would get even larger. So that's why we say it's a major impact to large regions. Okay. Now, we made a list of stations with the most background impact, and basically what this shows is some of them are the same stations, which is just random, but the difference in impact here is actually kind of interesting. If we look at the aerosol impacts, the base MDC of a station compared to its 95th percentile, we see these things range from a factor of not very much to a factor of 10 degraded or raised or degraded by background. But if we go to the Xenon systems and look at the top 12 stations there, they get 10 times worse to 100 times worse in MDC due to background. So that's another way of gauging the impact. Aerosol iodine-131 background is not that great, but the Xenon background is pretty profound. So let me get out of the way again. These are some of the most interesting results we got. If you look, we see for a 39 and 79 station network for Xenon, and for the barium and iodine sensitivities, this is the detection probability. And aerosol systems, which I've always been associated with, are great, but this kind of overstates the greatness, because in a given event, the xenons are orders of magnitude more likely to be released, or released in orders of magnitude greater quantity. So in fact, the iodine and barium, while they may appear to be more sensitive at a given release level, like 10 to the 12th to 10 to the 13th, the xenon is really the dominant signal. But the number of detecting stations is in this middle panel, and the number of reporting samples is in the right-hand panel. So each of these tells us that in order to have a confident detection, we're going to have multiple stations and multiple samples. Now, all of this is not bad, because we usually think about a release of 10 to the 15th or 10 to the 14th. Next generation systems could make this better by having just more samples, and in fact extend our sensitivity downwards a bit. Now let's work an illustrative example. Let's start by imagining this case I was talking about before, where we have 1% of the xenon escaping and 10 to the minus 5 fraction of iodine escaping. The detection probability for xenon, it's tough for me to get out of the way, detection probability for xenon is high, but this is a 79 station network. If I drop this down a factor of 2-ish, I would be at 50% or less sensitivity, where the iodine detection sensitivity is somewhere around 26%. So maybe you don't like having a detection probability for your overall network of around 50%, but adding in the 26% from the iodine actually makes it a pretty decent sum. That's the point I wanted to make. But the story on the number of detecting samples is not really great. The number of detecting samples for xenon for a 79 station network is 6.5, but that would only be about 3 on average for a 39 station network. Iodine is only 0.5. If we had a little more sensitivity, like a factor of 2 or 3 more sensitivity for iodine, we could on average have an iodine sample to add to a xenon sample in these cases where we would have a small release. So I think that actually bolsters the case that we need more sensitivity for iodine, and we actually have it if we will simply send those samples that are nearby in space and time to a laboratory, IMS laboratory for remeasurement. A low background laboratory could add a factor of 2 or 3 in sensitivity for iodine. So the next steps I think we ought to take based on our little study of the background, I think if we understood the background sufficiently well, we could lower that action level, which would repair the xenon network quite a bit. We could make additional measurements at IMS stations, like the second 40 stations, to see if our background estimates are correct. We could add local measurements like regional monitoring data, stack monitors, or temporary background campaigns, and further develop the support of iodine for the xenon network. That's the cross-signature support. I would like to do all of the above, and in particular run temporary science experiments that include all of these as much as possible at the same time. So we did a quick look at what kinds of places could support all of these things, and we came up with kind of a notional list. This is not necessarily the most objective list, but a notional list of places, and it's based on the presence of stack monitors and second 40 stations and so forth. And I'd really like to see a discussion of what these different locations could bring to bear. So with that, I'm ready to stop and take questions, and thank you very much for your time.
Thank you, Harry, for this excellent presentation. Should we have questions? Okay. Thank you very much. I wanted to ask a question, but you already anticipated, and it's related to how the next generation noble gas systems will be improving the situation. Harry, would you like to elaborate a bit more on that?
Thank you, Hakeem, and good morning, afternoon, evening, whatever, to all my friends. Well, first of all, I mentioned in the video that just taking more samples per unit time will help because it narrows the time window and allows you to have a better location when you're looking backwards. But a little additional sensitivity may give you a second isotope. And this study we did was all about one isotope, but having a second or third isotope gives you a lot of power. Everything about next generation systems makes this better. So I think that's probably the answer.
Thank you. Thank you, Harry. So we have a second question. So the question is about the methodology used for simulating the backgrounds.
I can take. Can you hear me?
Yes.
Okay.
Yeah.
Yeah. For
We lost your audio, Paul. We lost your audio, Paul.
Is that on now?
Yes.
Okay. Yeah, for iodine background, we just took IMS samples. We had samples at 72 of the 77 stations or so. For xenon backgrounds, we simulated rather than use measured values, and that was based on 181 reactor locations, and we simulated for a year, and we also included 12 medical isotope production locations with average published values. We didn't include research reactors, which in a couple of places might have influenced it, but it was a simulated estimate. And for a couple of stations, which we double checked it, we come pretty close at the 95th level of measured and simulated.
Thank you, Paul. We will take a third question before moving ahead with the second presentation. So the question is about the criteria that you would suggest for selecting the samples to send for laboratories for reanalysis in order to improve the sensitivity for iodine 131.
I'd love to answer that. The obvious thing, or there may be more sophisticated ways of doing it, but the obvious thing is if you have at a given location where you have xenon and aerosol, if you have xenon detect, then those aerosol samples should be sent for reanalysis to get a modest improvement in the iodine sensitivity. If you don't have them at the same station, then you would pick the adjacent stations at that time. There could be a more sophisticated way of doing it, but that's nearest neighbors in space and time is the short answer.
Maybe just a quick follow-up. It's actually the original question. How about if iodine 131 is not detected? Could, for instance, the detections at the co-located noble gas system trigger such a reanalysis of the particulate sample?
Yes. I think that's just the same question asked from a different perspective.
Yeah.
I think the assumption would be when we have detected xenon strongly in the past, there may have been an iodine signal that was there, but too low for us to detect in the field. So you would take those non-detect aerosol samples and send them to the lab.
Thank you, Harry. Thank you, Paul, for your additional clarifications. And now we go ahead with the next presentation. It will be given by Puni Taibi from the Iran Nuclear Regulatory Authority. And again, we have a pre-recorded video. Would you please?
Thank you for joining me in this oral presentation at SNT 2021. This presentation is about radioxenon isotopic ratios from activation of stable xenon in releases from nuclear facilities in relation to fission sources visualized in multi-isotope-ratio plots. Normal observation from fission sources have xenon 135 to xenon 133 activity ratios well below the screening threshold of 5. Some evidence has shown that besides of radioxenon from fission, the releases of activation-generated radioxenon can occasionally be observed at noble gas systems of International Monitoring System. Radioxenon emission from neutron activation sources have extremely high xenon 135 to xenon 133 ratios and may cross the screening threshold. If traditional radioxenon isotopes appear in IMS samples, they will interfere with the analysis. The previous study by Franziska Klimberg showed that the radioxenon signatures from HFIR reactor, which is high flux isotope reactor, are more representative of xenon activation than uranium fission. She also showed that it is feasible that HFIR source Thank you for joining me in this oral presentation at SNT 2021. This version,
So, 10-minute talk.
Thank you for joining me in this oral presentation at SNT 2021. This presentation is about radioxenon isotopic ratios from activation of stable xenon in releases from nuclear facilities in relation to fission sources visualized in multi-isotope-ratio plots. Normal observation from fission sources have xenon 135 to xenon 133 activity ratios well below the screening threshold of 5. Some evidence has shown that besides of radioxenon from fission, the releases of activation-generated radioxenon can occasionally be observed at noble gas systems of International Monitoring System. Radioxenon emission from neutron activation sources have extremely high xenon 135 to xenon 133 ratios and may cross the screening threshold. If non-traditional radioxenon isotopes appear in IMS samples, they will interfere with the analysis. The previous study by Franziska Klimberg showed that the radioxenon signatures from HFIR reactor, which is high flux isotope reactor, are more representative of xenon activation than uranium fission. She also showed that it is feasible that HFIR source is measurable at the USX-75 station, which is in Charlottesville. This plot represents the ratios of traditional radioxenon isotopes to xenon 133. Here is a clear difference in radioxenon isotopic ratios from fission and from activation. This part shows the ratios coming from fission for different kinds of nuclear research reactors. For the fission sources, the lead nuclide is xenon 133, which is clear here. And for activation sources, it is clear that xenon 133 has the lowest activity. Xenon 131M has the highest, followed by xenon 135. In 4-isotope plot, civil activations and nuclear explosion domains are separated by a discrimination line. On the left side of the discrimination line, there is one cluster around the equilibrium point, that is a fission cluster. And there are two distinct activation clusters belong to Vienna Tiriga and Texas Tiriga reactors. These two simulations of activation products seem not to be in agreement. This table shows the parameters of these two nuclear research reactors and also the annual release estimates based on the measurement. We apply origin and vary parameters to try to consolidate them. The origin results here use different irradiation and decay times. The results are found right in the middle between the two previous simulations. For our simulation, we consider thermal library of origin 2.1. Irradiation time is varied between 0.1 to 10 days. And decay time is varied between 0 and 1 day. We also compared the origin results with the annual release reports for HFIR, which are shown here by blue stars. This plot shows the ratio of argon 41 to xenon 133 and xenon 135. The origin results show best match with HFIR release reports for irradiation times between 2.4 hours, which are these purple triangle, and 24 hours, which are these green signs. So by these simulations, we get a more robust understanding of radioxenon from activation in research reactors. Now the next step is applying this knowledge to nuclear power plants or MPPs. So here we added the logarithmic average of annual release data for French nuclear power plants from 2002 to 2019. MPP release reports are found in the activation cluster. Now the question is, could MPP's release be dominated by activation rather than fission sources? We keep this question in mind and continue. Here are the annual release data for French nuclear power plants are presented. Many annual French MPP release reports are in the activation cluster. But for example, the Forsmark nuclear power plant from Sweden is not in the activation cluster. Now we plotted only data of French nuclear power plants which include the activation product Xenon 127 in their report. The Xenon 135 to Xenon 133 ratio is almost the same for all, but the metastable ratios is widely varying. At least all reports that include Xenon 127 are very consistent with the activation data. This plot shows the ratio of Xenon 127 to Xenon 133 and Xenon 135 for French reactors. The measurement data concluded from Klinberg paper and the origin simulation. Simulations are in good agreement with each other, except for one outlier. The French reactors data are by several orders of magnitude off from simulations. So activation is negligible contribution to MPP radioxenon releases which are dominated by fission. Now we know that HFIR is a strong source of radioxenon from activation. From 2006 to 2018, the argon-41 releases of HFIR show a declining trend. In the same time, argon-41 release of the spallation neutron source, or SNS, increased. The argon-41 releases of SNS reach almost the level of HFIR. So, knowing that HFIR is one of the strongest sources of radioxenon from activation, it can be assumed that spallation neutron sources may also be a strong activation source. So for the conclusion, we demonstrate clearly distinct clusters for fission and activation sources in 4 isotope plots. And we show that Xenon-133 is leader for fission, Xenon-135 and Xenon-131M are leaders for activation. More detailed origin simulations compared to previous studies reveal sensitivity to irradiation and decay time. Nuclear research reactors confirm as possible a strong source of radioxenon from activation. Nuclear power plants are very unlikely to be a strong source. Large spallation neutron sources can be a strong source. The next step is having a conclusion not only by the simulation but also with an equation. For this, I refer you to the poster P3.5 483 presented by Martin Kalinowski. Thank you very much for your attention.
Thank you, Pony, for the excellent presentation. As I can see, Boshwi, do you have questions? Yeah, let's see. It could be also just a comment. So, yeah, it's actually a question which you also anticipated in your presentation. So next, if there is any. Otherwise, let's go ahead with the third presentation of the RN part. I have the pleasure to share with you. Could you please screen share the? Yeah. Screen to screen to the left. Thank you. This presentation is about the updated status in terms of the novel radionuclide software applications that we are developing at the IDC. Okay. So the IDC engaged on developing new software application for modernizing the processing in both automatic mode and in interactive mode. And the projects aim at addressing a wide range of business cases, starting with completing the migration to open source to integrating the next generation of system technologies, but also introducing new analysis algorithms. So we'll be talking about Inspire, which is the new interactive platform for the radionuclide analysis. Then Autostrada for the automatic processing. GrandSim is a new Monte Carlo open source based for simulating the detection systems for both particulates and noble gas. And then we have the new web-based application, Aaron Toolkit, for sharing the data with NDCs. So we starting with the Inspire. Inspire project is now completed. It's phase 1, and we are in the process of extending to particulates within phase 2. It has the main functionalities for doing the interactive analysis of the radionuclide data. It is already used in the IDC operation since the last week of May. A month ago. And then the new version was also delivered to national data centers in November 2020 as part of the NDC box version 4. So in addition to the currently operated noble gas systems, Sauna 2, Inspire is also prepared to process data from all next generation noble gas systems. The version in the NDC box includes extra features which allow the users to download data, IMS data for any station, any technology, just from within the GUI. And then the other feature is for performing the automatic processing also from within Inspire GUI. Autostrada project has been mainly motivated by the need to get prepared for processing the data from next generation noble gas systems in a timely manner. And by next generation, we mean Sauna 3, Spalax NG, Xenon International, and Mix, in addition to the currently operated Sauna 2. The Autostrada implements the NCC algorithms, and recently we also integrated BGM software module, as this was delivered by our colleagues from FY Sweden within the Sauna 3 acceptance testing process. So Autostrada is now in the process of the final pre-release testing. By the way, we just switched the automatic pipeline in the IDC Devlan from BG Analyze to Autostrada, and we will be able to promote this to IDC operation in a timely manner so that the data from the first Sauna 3 system in Stockholm will be processed using BGM as integrated to Autostrada. Here are some plots showing the good agreement in the testing of Autostrada for the 4 xenon isotopes, and that's based on 1 year of Sauna data. GrandSim is the Monte Carlo simulation. Why Monte Carlo? Because this improves the analysis results in the radionuclide pipeline. The IDC has been using VGSL for generating the Monte Carlo parameters for almost 20 years. VGSL could not be distributed to NDCs because of its dependency to MCNP license. And that's what part of what motivated the new project GrandSim. It is GN4 based, And then the first alpha version was already provided to NDCs for testing in October 2020, and currently we are in the process of performing the pre-release testing by IDC analysts before releasing this to production. Some of the features of GrantSim very quickly, so it can be used in database mode where the input is read from DOTS and GATS databases, but it can also be used in offline mode. The software has a feature for optimizing the model in fully automated mode, and that's one of the major steps when it comes to doing Monte Carlo simulation. And that reduces significantly the simulation time in the sense that the user doesn't need to go through iterations for optimizing the detector parameters in comparison to the experimental calibration. So output, GrantSim is producing cascade summing correction for any isotope, well, any isotope which suffers from this issue. It also produces the isotope response function, which is like a normalized spectrum to the key line. GrantSim knows also how to produce simulated spectra for any composition of in terms of source composition and activity concentrations, and this produces the output in IMS 2.0 format so that it can be further processed in the using, for instance, the NDC box or whatever processing tools. So Aran Toolkit, this is the last part. The idea of Aran Toolkit started at the expert technical analysis and the special studies like 2 years ago, almost. And the aim is to further empower the national data centers by allowing easy access to the IDC external database just from a GUI, by selecting the time frame and then the station of interest. The tool can already answer the question, what radionuclides have been detected? And this is available for both particulates and noble gas. In addition, the tool also provides time series of the background of detections, including the activity concentration, but also the categorization information in one plot. And this can be exported to CSV format, for instance. Then, in addition, the tool provides plots for the isotopic ratios, both xenon and noble gas and particulates. And then on the screen that we have here, for example, we have the 4-isotope plot in the lower part with the red annotations indicating the screening flag thresholds for the two ratios. And this is very useful when it comes to radionuclide event screening by national data centers within the CTBT verification related activities. Aran Toolkit can also provide a snapshot for any day, and that contains the information on detecting stations, including the categorization level. So on this map, it's for noble gas. That's why we see red yellow, which means one of the samples was level C and the other one was level B. Then yellow green means one of them was level B and the other one was level A. This can also be used in animated mode for any time frame, and that could be also used for tracking any radionuclide like if we have any episode of detections, we can run Aran Toolkit for the nuclide in focus and the time frame of interest, and that allow to gather very quickly, just with a few clicks, very valuable information for further analysis. So to summarize, Inspire is now deployed in the IDC operation, and it is also available to NDCs. It handles both current and the next generation of noble gas systems. Autostrada is about to be promoted to the IDC operation for replacing BG Analyze, and that will also be used for both current and the next generation noble gas systems. The Monte Carlo, it's the first time that the IDC developed an open source Monte Carlo simulation tool. The functionality for particulates is completed, and then the alpha version was delivered to NDCs, and it is now under final testing at the IDC. Aran Toolkit is now a web-based application. This was delivered in March 2021. It's available to all authorized users through the single sign-on, and it covers particulates and noble gas. Thank you. That's all I have, and we will take a few questions. Thank you so much. Yeah. So we have the first question. Have you used GrantSim for creating the spectra for exercises? This seems like it could be very useful in creating OSI and injection, triggering data, expanding. Yeah. Thank you for this excellent question. So indeed, that would be actually one of the good use cases of GrantSim, is to simulate for like OSI on-site inspection, but also for proficiency test exercises. It could be also used for NPEs, like NDC preparedness exercises. That was the case in the NPE 2015, but at the time we used the VGSL, and because of the complexity in the source term, we needed to split the radionuclide list into like I think 3 simulations, and then we combined them again. But with GrantSim, part of the stress testing is that we took the whole source term from NPE 2015 and made sure that GrantSim can handle all that in one run, and that worked fine. Then we have a second question, or is it a comment? Yeah, thank you for the nice words. We are doing our best, but again, this is like a team effort, and by team I mean both the PTS, but also the colleagues from the national data centers, and we keep improving based on this very nice interaction. Thank you. I think that's all we have. Thank you. We are sharply in time. We will now switch to the SHI part in a few minutes. Thank you again for joining this this session. Thank you.
So welcome to the second part of this data analysis algorithm session. I'm Chris Saragiotis. I'm with CTBTO, and with me is my valued colleague Sam Korbani, and lead analyst, who will be helping me with the questions. So without any further ado, let's go ahead with the first presentation. I think it's a pre-recorded one by Claire. Yes? So let's go ahead. Thank you.
Hello everyone, my name is Claire Labonne and I will present some multi-component seismic aware analysis to improve event detection and characterization. This work was done through the collaboration of CA with some colleagues from NASA. I predominantly perform using multiple vertical sensor with a single 3-component seismometer co-located at one site. The deployment of fully 3-component seismic arrays, such as access array or splits array, offers the possibility to take additional advantage of the currency on the horizontal component. For the case of ACE wave, this has a potential to significantly improve the detection and characterization. Despite this, 3C arrays are currently poorly exploited. And in this study, we demonstrate improvement in terms of event detection using IMS 3C array, and we investigate solutions to efficiently use the currency of the horizontal component. In this figure, represent the detection obtained automatically using PMCC, progressive multi-channel correlation array processing over 1 month of data recorded by access array, which is the north part of Norway. On the left, this is a result from the vertical component, in the middle from the north, and the right from the east component. If we compare these 3 polar plots, we can see that there is some azimuth and velocity area which are more illuminated from, for example, here from the east component than the vertical component. This illustrates the complementarity of the horizontal and the vertical component. In addition to this complementarity, if you have a look at the number of detection, we can see that we are more detection in the north component and the east component than the vertical component. This illustrates the huge potential of the horizontal component. But now, to optimize the use of the horizontal component, the north and the east components can be rotated into a radial and transverse direction, which is aligned with the azimuth of the propagation. This work is built on previous work, which already look at using such radial and transverse coordinate system in order to improve phase projection and separation. In this study, we are going further by performing 3-component PMCC array processing analysis by using P-wave azimuth detection in order to rotate horizontal component. The novelty here is the use of 3C components through a concatenation step in order to take advantage of the result over all the direction. And this 3C array processing was compared using a vertical only analysis. The second approach of the analysis is a prototyping of ray coordinate frequency wave number analysis by looking at prospective LTQ ray coordinate rotation through a grid search by taking into account different azimuths and incidence of the ray. This approach was verified using a set of phases from the NASA reviewability. So let's go into detail on the first approach called 3C ZRT PMCC analysis. So an array processing using the vertical component only was first performing using continuous data over 7 months of data. Then we select each potential P wave. On the right, we can have an example of potential P wave, which have a velocity higher than 6 km per second. Here we have the apparent velocity, and here we represent the azimuth. For each potential P wave, you use the detected azimuth in order to rotate the waveform to the radial and the transverse direction. And then we reprocess the reprocessing using these two new directions, the radial one and the transverse one. Here we can see that the S wave is mainly visible on the transverse direction. And then we process to a concatenation step in order to combine information we have on the radial, transverse, and vertical direction. So here now we can see clearly the P wave and the S wave in only one figure. Then we selected, as we can see here, only phases which come from the same azimuth as the P wave. So in this example, you have only two phases, the P and the S wave. Then, after the phase sorting labeling, we process a kurtosis phase picker. So for each phase, the component with the best SNR is chosen for the picking process. In this example, the P wave are using the radial beam waveform, whereas the S wave, we are using the transverse beam waveform. Once we have the P and the S peak arrival time, in addition to the P wave azimuth, we are now able to locate the event. So this 3C process was done through 7 months data, in addition to a classical or one component process. So now if we have a look to the results. So on the left, you can the result from 1C process and the right from 3C process. If we compare both figures, both located events, you can see there are more events along the spreading ocean ridge. And now if we zoom on the source part of access, we can see the main most of the located events are located close to the identified mine area. We also see some events located along the coast. We have some phases misidentification, which appear here with a double cluster in the direction of a certain mine area. But now, if we want to look, if we want to compare both processes, just by looking these two figures is quite difficult, though. So I propose to look at the number of detected events over 7 months of data. So here it's the percentage of increase, and if we took all events, we can see that the improvement is quite important. We have more than 53% of improvement. This improvement, it's significant. It's particularly significant for phases which have a signal over noise ratio larger than 3. This effect is due to the fact that some event which has already detected by 1C process have, when you are using 3C process, we have a larger SNR because the horizontal components have larger SNR. Let's move to the second approach by using the way coordinate system called LTQ. The improvement of this LTQ compared to the previous radial transverse rotation is the fact that we take into account the incidence of the wave, which this led to a 3D rotation. This way coordinate system permits to have a full separation of P, SV, and SH wave. Our approach, it was done through a grid search over a different couple of angle of incidence in back azimuth. And for a given incidence in back azimuth, we just rotate the waveform, we perform the frequency wave number analysis, and so at the end we have an estimation of the semblance estimation, which is a normalized measure of the covariance. And we'll repeat this for each couple of incidents in back azimuth. So we perform this using one event from the Kiowana mine, which is located at 2.5 degrees from the access array. So the figure here represents this semblance improvement by comparing the semblance obtained from the longitudinal component, the Q component, or the transverse component, relatively to the vertical component. One line corresponds to a given back-azimuth and incident. So here, if you have a look at the 10 first line, we can see all correspond to the same back-azimuth, but for different incidents. The benefit can be seen particularly for the P wave on the longitudinal component, whereas for the S wave, we have a significant improvement on the transverse direction. If we apply this 3C rotation approach by reprocessing all phases from the NASA review bulletin from 5 months of data by looking at the direction leading to the maximum semblance over all possible direction in the 3D space. This direction will be called D direction, and we expect to have this direction longitudinal for the P wave and orthogonal for the S wave. So here is the result for the P wave on the left and for the S phases on the right. This is a comparison of the back-azimuth, the difference in terms of back-azimuth and apparent velocity between the D direction and the vertical direction. So these both are largely consistent for all review phases. We have only 4 outliers which need some investigation. But for both P and S wave, we have significant improvement in semblance, which are represented by the color. So when you are a dark red color, which represents a significant improvement in terms of semblance. So if we have a better semblance, we have a better NCNR improvement, and we have a better estimation of back-azimuth and slowness. Here you can see a summary. So in this presentation, we see clear benefits by using IMS 3C array for event detection and localization. We have a clear SNR improvement for both P and S wave, and we have a better capacity of detection. On the right, you ongoing work in perspective. The first one is we are currently looking at the IDCX and NORSA review bulletin in order to be able to quantify the improvement in terms of localization performance. We are also planning to look at the Pmcc approach by using polarization of P wave in order to estimate the incidence of the wave and be able to rotate the waveform into the wave coordinate system. The second approach presented here still needs some refinement, which are listed here, but I think the concept is good. Finally, we plan to apply 3C array processing analysis on smaller aperture array because we know that such smaller array has the advantage of the 3C array will be significant, and also because it will permit to locate events using not only a single array but using 2 arrays. Thank you for your attention, and if you have any question, with pleasure, I will answer.
Thank you, Claire. We don't seem to have any questions yet from the attendees. If I may ask maybe something, some question comes. So is this something you think that can be done in real time, this rotation and semblance investigation?
Yes, can you hear me?
Yes, we can hear you.
Okay. The first approach I present in my study, which was the Pmcc approach. I think this kind of approach we can do it in real time.
So, I mean,
But the second approach, which has much more computationally, the second approach with the AFK analysis, we cannot do in real time.
it would be interesting to see this because Asimov estimation from three-component stations is a challenge for us too. So it will be very interesting to see how this would work for us as well. Alexander, would you like to ask maybe something?
Yeah, since we don't have a question, can you hear me? And I should see.
Yeah,
Okay.
I can hear.
Yeah, one of your conclusion I saw the difference between P wave propagation and polarization. It reminds me of anisotropy that could cause this among other reasons. And I wanted to ask when you use the two component of the shear wave, the SH and SV. So in the cross, you may have a strong anisotropy that caused a difference on the arrival time of these two. So do you take this to account, or have you planned to take this into account? Just dig into more details.
Sorry.
Or can comment that all of your assumption is based on isotropic velocity model. So is it that, or?
This is done, yeah. We assume that yes, that the radial direction is in this approach is taken from the P wave. So yes, we assume anisotropic. Yeah. Yes. Yeah, I did some previously. I did some research, but by looking at because in this approach I took the direction of the P wave. But if you don't took this direction, you can try to apply array processing over a different direction, arbitrary direction, and look which one is the best. And sometimes, yes, in case of anisotropy, you could the best direction could be not the one from the P wave, but you cannot do it using in real time. It will too much consuming, but it's an approach. You can do it if you want to go further in a specific event, which a strange event where you have where you know that you have anisotropy.
Thank you, Claire, for this very interesting presentation and your answers. Let's move on to the next presentation, please. I think the presenter will be David Schaff, and it will be a live presentation.
It should be a pre-recorded presentation.
It's a pre-recorded. Okay. So. Would you like to share your presentation, or would you like us to share it, David?
If you have it, it might be better. I wasn't able to get the sound to play before, but.
Okay, so let's do that. Sorry, can you ask? Does it have sound? Yes, he will present. We'll just share the presentation. Okay. Thank you. You can.
Do I have it?
That's what I'm told. Yes.
I saw it come up on your screen. I'll try to share it on my screen.
You use the arrows on your keyboard to control slides? Do we maximize it or is it? Can we maximize it? Oh, okay. Okay, so with a delay. We cannot hear, we don't have sound, it seems. So, David, you're sharing?
I'm sharing, but I don't know how to do the sound.
Yeah.
Can you ask him to stop sharing?
Can you please try, can you please stop sharing? We will try something else here.
Sharing. Is there an option for audio? Let's try again. Okay, he doesn't.
You don't need to share it, but you will be able, using your arrow keys, to control the slides that are presented. Is this a presentation or is this a video? Because I see. Move to the next presentation until this issue is resolved here from the technicians. Mike, are you ready maybe to?
So are you guys going to share the video or do you need me to do that?
You have a video. Can we share Mike's video?
Having three-dimensional. Yes.
Hello, my name is Michael Bonneau and I'm from Los Alamos National Laboratory. Today we'll be speaking on comparing higher dimensional velocity models for seismic location accuracy using a consistent travel time framework. I would first like to acknowledge my collaborators from Sandia National Laboratories listed below. Here's a brief outline for my talk today. I'm going to be giving some introductory information, including the software used for the study and about source-specific station corrections. Then go into discussing a travel time framework for the 3D lookup surfaces built using a program called Geotest. Then some considerations for using these surfaces, some actual tests of using the 3D lookup surfaces with an IMS network, and then also what is needed from a 3D model developers in order to use these surfaces. For an introduction, I wanted to say historically, location algorithms have relied on simple one-dimensional velocity models for vast seismic locations. The speed of these 1D models makes them the preferred type of model to use mainly for operational needs. Higher dimensional models are becoming more readily available from the scientific community and provide significantly more accurate event locations over 1D models. The computational requirements, however, for these models tend to make their operational use prohibitive. Comparing the location accuracy for 2 and 3D model seismic velocity models tends to be problematic because each model is usually determined using different inversion parameters and ray tracing algorithms. And if you attempt to use a different ray tracing algorithm than the one that was used to develop the model, it almost always results in poor travel time prediction compared to the algorithm used when developing that model. So populating consistent station phase lookup surfaces with the actual predictions from the relevant ray tracing algorithm associated with an Earth model removes an inconsistency that can lead to problems when using 3D models for travel time prediction. So using that 3D travel time framework would also enable fair and consistent comparisons of location accuracy for various higher dimensional velocity models. I'm going to spend some time discussing the software used for this study. Geotest is an open source gridding software developed by Sandia National Laboratories and is publicly available at the website shown here. A geotest model is comprised of 2D triangular tessellations of a unit sphere with 1D radial arrays of nodes associated with each vertex of the 2D tessellations. Variable spacing is supported both geographically as well as radially. See the graphic on the right here. It can store just about any type of spatially defined values, including Earth models. Some examples are given here. Station-specific travel times, which is what we're talking about today, and other models and/or predictions, like amplitude. For doing the relocations and predictions using the 3D lookup surfaces, we use the publicly available local 3D and PCAP programs, which are on the Salsa 3D Sandia website. Local 3D is used for locating single events, or can be used in master event mode, and using a variety of seismic velocity models. It's based on the CSS 3.0 schema data definitions and reflecting its origin in the seismic monitoring community. It can read-write using Oracle database tables, flat files, and data can be input as custom formatted text with appropriate columns. It is multi-threaded and can use various model formats like 1D travel time tables from TAU-P, 3D lookup tables as discussed here, and 3D ray tracing. Pcalc is a prediction calculator that can compute various things like travel time, azimuth slowness, uncertainty. It can extract model values from the user-specified coordinates and can compute ray geometries using ray bending for a 3D geotest Earth model. It has the same model types as those available for local 3D. What has commonly been used in travel time lookup tables is a format called source-specific station corrections, or SSSCs. The IDC uses SSSCs to do travel time predictions for regional phases, and they are generally a lat-long grid of corrections to the ASPE91 model plus uncertainty. The IMS is a relatively static network, so this is computationally feasible and fast. This is the current framework in which the regional seismic travel time model and predictions will be used at the IDC. However, they only have corrections at a single depth, for example 10 kilometers. It is a rectangular grid and can cause problems at the poles, and the grid spacing is also not equal, and the correction surfaces produced are not equidistant from the station. So compare the SSSC grids below with the triangular tessellations produced using geotests. We can overcome the ray tracing algorithm issue by using geotests for the travel time framework, allowing easy storage of 3D travel time data. We generate one lookup table for every station phase combination by using the exact ray tracing algorithm that is preferred for the model. Surfaces are generally applied as corrections to a simple 1D velocity model like ISP91. Geotest permits variations in event depth as opposed to legacy SSSCs and is optimized for depth based on seismicity patterns from the ISC catalog. It can also include estimates of travel time uncertainty and empirical travel time corrections if the user chooses. Having a common travel time framework for location allows individual 2D and 3D models to be compared in a fair and consistent manner. On the right is an example surface for the IMS ILAR array showing travel time corrections to the AK135 model, and the inset shows the travel time path-specific prediction uncertainties. Some considerations for building and using 3D lookup surfaces. Again, you have one surface for each station phase combination. So for example, you can build a first P and a first S surface as combinations of P and PN or S and SN respectively. For this talk, we built first P surfaces for the IMS network. Other surfaces could be built for phases like PCP, PKPDF, and PKPBC, among others. You can use a correction surface for a nearby or legacy station or array elements by defining a support map file that maps one surface to the other stations. We used a 10-kilometer distance for associating a surface to another station. Because the surfaces built here are travel time corrections, they are less sensitive to small station separations. For example, a surface for the GEYT array in Turkmenistan could be used for station ABKT, the legacy GY array, and the station VAN. The geotest framework is also flexible in building the type of tessellation for the surfaces. Using the geotest builder software that is being incorporated into Pcalc, users can customize how the tessellation is built. If needed, a tessellation can be refined around a station or in any place specified for denser points, for example at close-in station distances or in tectonically complex areas. Surfaces could also use one common grid to save memory. So the images on the right are examples of different tessellations that could be used. The next step is to show the accuracy and size of geotest surfaces versus 3D ray tracing. This example uses the SALSA 3D model, which is publicly available on the Sandia website shown previously. We randomly selected 1,000 pseudo events, which are red on the map on the lower left. Using all primary and auxiliary IMS stations, which are in blue, we predicted travel times for the first P phase. We only used event station paths from 0 to 100 degrees distance. That gives about 92,000 paths. We tested geotest grid sizes of 1 degree, half a degree, and a quarter degree, all with 5-kilometer depth spacing. We compared the predicted travel times using full 3D ray tracing, or Bender, to those from the 3D lookup surfaces. On the right are some plots of statistics with distance and the difference between Bender and the lookup surfaces. For the 3 chosen geotest grid spacings, we plot the mean and standard deviations, which are in black, and the median and median absolute deviation from the median, or MAD1, which are in blue. The labels are the total memory size needed for the 151 surfaces, as well as for the approximate size per surface. The MAD1 values go from about 16 milliseconds for 1 degree to about 6 milliseconds for half a degree and 2.6 milliseconds for a quarter degree. Using the half a degree grid, we relocated actual events from the IDC reviewed event bulletin using event locations that are known to within 5 kilometers or better, which are GT5, and there are 2,292 events here. Relocating using both Bender and the 3D lookup surfaces, we compare the mislocation of the relocated events to the GT event epicenter. On the bottom left, we show a map of the events colored by which method had the smallest mislocation. Red is for the full Bender, or ray tracing, and blue is for the 3D lookup surfaces. They are randomly plotted and show no specific bias of any one method over another. On the right is a one-to-one comparison of the mislocation. There's about a 50-50 split between the number of events favored by full ray tracing, which is 1,127 in red, and the 3D lookup surfaces, which is 1,164, which is blue. The mean is 0.29 plus or minus 10.4 kilometers, with the median being negative 0.01 plus or minus 0.41 kilometers. So there are some outliers obvious here, but very few. This is a zoom in going from 0 to 50 kilometers distance and showing a 2D histogram. As you can see from this one-to-one line that most of the events fall within on that one-to-one line, with almost one-offs as you move away from this one-to-one line. The memory requirements for the surfaces are quite manageable. In this study, we rotated each tessellation grid so that a point was always located at the station location. We also used a half a degree grid out to 100 degrees distance from the station. To minimize file size, you could also generate a single global half a degree grid everywhere that is used for each station. The grid itself would be about 140 megabytes. One station and phase of data would be additional 20 megabytes. A total of 150 stations for 5 phases would be about 15 gigabytes. This would vary, of course, based on depth spacing of the grid. With 1 terabyte of RAM, you could easily hold about 50,000 station phase surfaces. So in conclusion, many 2D and 3D global velocity models are publicly available for use in comparison, but do the developers provide the algorithms for calculating travel times and predictions uncertainty for their models? This is required for the next steps. 3D travel time uncertainty lookup surfaces can be built for a set of stations and phases for relocation tests. Comparisons of predictions using full ray tracing show comparable values, and relocation tests suggest a 50-50 split between methods for location accuracy. Lookup surfaces could also be optimized for stations to reduce interpolation issues if found. The memory required for reading lookup surfaces is relatively small. Location algorithms like Loco3D could read in only those surfaces that are required, or a system could hold all of them in memory as a service. 3D lookup surfaces can provide a way to allow consistent, fair comparisons of velocity models used for location. A set of extracted grid values could be made available to model developers to populate using the ray tracing travel time prediction algorithm that is appropriate for their model. Predictions from developers allow production of new 3D lookup surfaces, and all these predictions would be based on the same locations in a grid. One caveat, it would be generally unknown whether models were developed using IMS data themselves, so there could be a circularity issue. I'd like to thank you for listening to my talk today. Please contact me if you have any questions.
Thank you, Mike. We're running a little bit late, and since we do not seem to have any questions from live questions from the audience, maybe we can move on to David's presentation. I'm told that David, will you be able to share your presentation?
I'll try.
Okay.
I'm looking for the microphone that Mike talked about. Do you hear me?
Can you click on the slideshow to have like a full screen view?
Mike said there was a microphone that I'm not able to find.
F5.
It's when you first select PowerPoint to share that window as a little microphone on the top right. You would have to do that. You're already sharing, so you have to do it before you share.
Yeah.
Maybe that's it. Okay. Oh, welcome to my talk.
Okay.
I'm going to talk about detection results we have in and near Mongolia and relocations. We used about 1,000 master templates from the LED and used a combination of array stations and single 3-component stations from the IMS arrays and at IRIS for 5 years of continuous data from 2012 to 2016. We ran a correlation detector for events in and near Mongolia in the green polygon area. We detected about 33,000 events that we were also able to locate in cluster locations. Then we went back and tried to do cluster locations. We need 4 stations to do a location, but not enough stations were in the detected catalog to do locations for a significant number of events. So we went and selected all the stations available at IRIS, which was a sparse regional network, a temporary network that Lehigh University deployed in Mongolia, and the dense KNet network in Kyrgyzstan. We selected window data to make measurements for high resolution locations. And it saves computation time when we don't have to run a correlation detector on all these stations. So the location results for Mongolia are comparable to other regions that we had for all of China in Wenshan. The mean 95% confidence error ellipses for the semi-major axis was 280 meters. This standard deviation of the residual sigma res 0 from the starting locations to the relocations went from 2.33 seconds down to 0.07 seconds, and it was a factor of 33 times improvement. Mongolia and Wenshan were detected catalogs. We detected new events. All of China was the annual bulletin of Chinese earthquakes that we didn't do in the cluster. We looked at time of day for these 12 large clusters ranging from 800 to 6,000 events. And 10 of these 12 clusters have 97% or more of their events occurring from working hours from 9 a.m. through 5 p.m., shown by the green lines on the plot on the left. And also day of week plots show that these are man-made events. 8 clusters have less events on the weekend, 30% or less events on the weekend. In some cases, they have uniform events throughout the days, but the fifth cluster had 1,000 events occurring at 12 noon and 233 events occurring at 6 p.m. The next 12 largest clusters also showed that they're man-made with time-of-day plots and day-of-week plots, except for one earthquake cluster that had more random origin times and hours during the day. The x-axes are the 24-hour day on the time-of-day plots. So from time-of-day plots, 9 hours from 9 a.m. through 5 p.m., we would expect uniform random origin times to have 37.5% of the events occurring within that time window. And what we find is 94% of clusters with 30 more events have 70% or more of their events occur from 9 a.m. through 5 p.m., which is a high number of clusters that we would classify as man-made that have a large number of events. And then there's different statistics for that, for different values, but this represents the first 50 clusters and 31,000 events out of the 32, almost 33,000 events, which is 96% of the seismicity, and it represents 16% of the clusters out of the 316 clusters. Events that have 4 or more, clusters that have 4 or more events also have a large majority of their events occurring between 9 a.m. through 5 p.m. for different levels of statistics, and it represents basically we have about 97% of the events that we can classify as man-made with 4 or more events, and 75% or more of the events occurring from 9 a.m. through 5 p.m., which again, random origin times would be 37.5%. So to plot it on the map, we have blue circles with 4 or more events in a cluster at 75% or more that we would consider man-made occurring from 9 a.m. through 5 p.m. And then cyan circles are the opposite of that, either 3 or less events in a cluster, or the cluster has less than 75% occurring during working hours. And the red stars are clusters with 30 or more events in a cluster and during working hours. So it occurs in areas that are known to have large mines in Siberia, Russia, and also Mongolia and Kazakhstan. The cyan circles, we would imagine that those are earthquakes, and blue and red, we imagine those are man-made. Here's some plots of absolute locations for the LEB for the different clusters. One cluster on the left, one cluster on the right, and the top panels are LEB absolute locations, and the bottom panels are relative LG correlation locations. The map axes are on the same scale, and it's a fairly large box containing the scatter of the absolute locations. We have a significant reduction in scatter of the epicenters in map view with the relocations, and the 95% confidence relative location errors are less than a kilometer in both these examples for these 2 clusters. We have some more examples of large clusters. With these clusters have about 1,000 events each, and there's some strange behavior in the LEB locations on the cluster on the left, and then the relative locations are really good locations. It's 210 meters relative location errors on the left, and there's comparing the absolute locations to the relative on the right cluster. There's 27 kilometer mislocations for the LEB absolute locations, and the relative locations on the right have 0.5 kilometer errors. With some more examples of clusters, the cluster on the left has 46 kilometer mean mislocations compared to the relative locations, which have 240 meter relative location errors. And there's about 1,000 events in each cluster. Zooming in detail, you see there's tighter subclusters in a 6 kilometer box. Some of these events. Here's another cluster with more structure and detail, with certain events occurring closer to each other, this time in a 20 kilometer box. And so now we plot the centroid location from the absolute locations of the cluster as a red dot, as a mean cluster location on satellite imagery from Google Earth. And we see that the brown areas are surface mines spanning several kilometers, and the green areas are vegetation, and the mean cluster location plots on top of the mine. The length scale on the bottom is 2 kilometers, so it's pretty close in terms of absolute location as well for this cluster. Here's another example with cluster centroid plotting about 8 kilometers from a mine, and the mine is the brown areas. Here's a cluster within about 1 kilometer of the mine is the brown areas. Here's a cluster plotting within 2 kilometers of a mine. It's the lighter areas on this map. You can see the roads. And here's a cluster that plots right on top of the mine again, the lighter areas. And then the final plot, we have 4 clusters in a larger mine with four smaller mines up that are lighter areas that match the 4 clusters, and they mislocate about 15 kilometers. So here are conclusions. We have about 1,000 master templates detecting about 33,000 events in 5 years, 33 times as many. We have a sparse regional subset of stations that can be used to verify at 2 or more stations to save computation time. And 95% confidence ellipses have averaged 280 meter semi-major axes. Many clusters at mines have 97% or more of their events occurring from 9 a.m. through 5 p.m. local time. Many of these mining clusters also have 30% or less events on weekends. 97% of the events we can say are man-made. Comparison of the absolute locations has mean scatter of 14.5 kilometers and maximum of 46 kilometers. In comparison of absolute centroid locations of clusters shows 9 out of the 14 largest man-made clusters plot on top of mines or have mislocation biases of 1 kilometer to 15 kilometers. Thank you.
Thank you, David, for the presentation. We finally managed. So we don't have any questions from the audience. Was that one? Sure. Okay, so. So the question is if the error ellipses usually contain the mine location.
We don't have error ellipses for absolute locations. It's just for relative locations. So the absolute locations were taken as the mean of the cluster, and we don't have an error estimate on the absolute locations.
So they were, yeah. So, yeah. Okay. So unfortunately, we don't have time for any more questions. We're about to be kicked out from the next session, participants. Thank you very much, everybody, for your presentations. Apologies for the mix-up that happened with the video, and we hope you enjoy the rest of the S&P conference. Thank you.